Hello, welcome to the next section. Like I said, this next section, chapter two, I suppose, if you want to call it a chapter, is all about light. Last time we talked about how we measure outer space in terms of light years. And that has to do with how much distance light travels over a certain amount of time. So this whole section is just focusing on light. It's an integral part of studying astronomy. And if we don't understand light and how light works, it's difficult to talk about the way things are moving up in outer space. Scientists use what we know about light here on Earth to understand what's happening out there. So, because we understand the way light works here in our regular day to day lives, we can take that information and understand, well, if light is affecting that particular star, in this way, then we can assume some things about the star. What kind of gases the star is made of. Maybe if light is passing through the atmosphere of a planet, we can figure out, well, what is that planet made out of? Is that star moving closer to us? Is it moving further away from us? How bright is that star? What color light is the star giving off? All this kind of stuff. So we have to know about light. Now, light travels in a wave. Maybe you've had a class where you've talked about waves in the past. I would say more than likely you've had a class where you've talked about waves in the past. I'm going to try to make this quick. Uh, there are three main parts of a wave that we need to understand in order to get how a wave works. Now, like I said, light moves in a wave pattern, like you see the one here on my screen. Just like how any particle can move in a wave, you see water move in waves a lot. Sound moves in waves just like this, and so does light. There are three main, the word escapes me, parts of a wave that we're going to be looking at. And I've got them over here: amplitude, frequency, and wavelength. Wavelength and frequency slightly more important for our discussions, but all of them necessary. Let's start with amplitude. Now, this particular wave here, I just stole off the internet, but it has an amplitude. That amplitude, we'll represent it with, let's represent it with red. Amplitude is the height of the wave away from this baseline. So we have this baseline that would be sort of the middle of the wave. However high that wave gets away from the base point, we call that the amplitude of the wave. I will just mark it with the letter A. The amplitude. It directly corresponds with the strength of the wave. The stronger the wave is, the bigger the amplitude it's going to have. So here's the exact same length, the exact same amplitude. We'll represent that with our letter A. We could have a wave with a weaker amplitude. Let's draw one. Let's draw a green one. Oh, here we go. Ready for this? I'm drawing this with a mouse, so don't make fun of me. Mm-hmm. Boop, bam, pow. Oh, beautiful. Da Vinci wishes. All right. This wave, this green wave, also has an amplitude. It's just that amplitude is a lot smaller. It's only this big with a lowercase a. Oh boy, here we go. Bam. Smaller amplitude. It's just the distance from to the peak of a wave from that baseline. Great. That's amplitude. Frequency. Frequency is the number of waves that pass over a certain amount of time, usually in 1 second. How many waves pass? How quickly the waves go by over a certain amount of time. This wave, can I delete this green one? Sorry, green wave, you have to perish. Die, die, die. This particular wave has three waves that pass in however long this would be. Let's just call this amount of time something other than red. Let's call yellow. Let's call this amount of time all the way over to here. Let's call it 1 second. Okay. Terrible. Looks like a kindergartner. So let's draw a different wave. We can give it roughly the same amplitude, but a higher frequency, meaning there are more waves in that same amount of time. It's good enough. The purple wave here has a higher frequency, meaning those waves are sort of squished together, and there are more of them that come in the same amount of time. So this one has what, 1, 2, 3, 4, 5 waves in that 1 second, versus the blue wave, which only had 3. Frequency. It's how many waves show up over a certain amount of time. Oh, I was a fool. All right. I'm sorry, wave, but you got to go. You got to go. All right. Last thing. Die. All right. Last thing, wavelength. It's the distance from the peak of one wave to the peak of the other wave. We call this a wavelength. We represent it with this Greek symbol lambda, but if you just call it wavelength, I won't get mad at you. It's a distance from one crest of the wave to the next crest of the wave. The smaller the wavelength, the stronger the wave is. So if I draw a wave that looks more like this, look, it's not great, but it gets the point across. If I draw a wave that looks more like this wave has a wavelength of this much distance. Call it lambda 2 versus lambda 1. This wavelength is obviously much longer. That wave is weaker. The bigger the wavelength, the weaker the wave. Okay, so big wavelength, weak wave. Short wavelength, like this, is a very strong wave. We'll see that the shorter the wavelength is, the more powerful radiation comes from that particular wave, which is what we're going to be talking about here in this next section. Delete all this. Delete. All right, that's wavelength. Sorry, we're going through these kind of quick. I'm operating under the assumption that you've heard these terms before. Last thing here for this video, and we'll do the EM spectrum in the next one. The speed of light. When we talked about light speed a little bit. It is useful when we're talking waves and when we're talking distance. Remember, our baseline for light was it gets to the moon in 1 second, the moon from Earth in a matter of 1 second. But it does actually have a speed, just like how your car is driving 55 miles per hour, or you're walking at whatever, 2 miles per hour. The speed of light has a speed. It is, I'll give it to you in meters per second. Oh, let's just type it out because speed of light equals a little less than 300 meters per second. 300 million meters per second, which is very fast. For reference, a meter is, sorry, I gotta stand up and show it off. I don't know, a meter is roughly yay long. Okay, so any beam of light, any light moving, is able to move 300 million of these in 1 second. So the light that comes off my phone when I turn on my flashlight, bing, it could travel 300 million of these in 1 second. So ready? 1 Mississippi, bam. That light was able to travel 300 million of these in 1 second. Incredibly fast. Miles per hour. I want to say 300,000. Let me just look it up. Speed of light, miles per hour. That's kilometers per. No. I don't want that. Speed of light, miles per hour. 186, according to the first Google search, 1,000 miles per hour. Also, pretty quick. Great. All right. So that's our baseline. Remember, when we measure things in outer space, typically we're measuring them in a distance of light years. So light travels 300 million meters in 1 second. Think of how far it can travel in a year. Okay, that's 1 light year. Our next closest star from the sun is 4 light years away from us. And the Andromeda galaxy is 4 million light years away from us. Incredibly far distances. All right. Next one, we'll talk about the electromagnetic spectrum, different types of light, some stronger, some weaker. The light that we can see, no spoilers, but you can see it up here in the corner. You can zoom in on it, but I'm not going to. You can look at it in the next video. Then after that, we'll talk about the Doppler effect of light. Talk about how we can tell whether stuff is moving towards us or away from us up in outer space. All right, that'll be it for this one. I will see you in the next one. Bye.